what I'll do is describe what a PID controller is. Um, is there anyone who's not ever heard of a PID controller? Okay, just a few people. Okay. Um, is there anyone who's never worked with a PID controller? Okay. So, oh, good. So that'll be helpful to some of you people. Okay. So, oh, and what we worked on last time was this pull-in actuator, and on the example that we had, it was what we're going to do next. We were going to have it determine where the point of pull-in is today, but and we looked at the resonant frequency and the modes last time, but I found a much better model that actually has the contact. So it not only pulled it in, but it had contact so the structures didn't pass through each other. So we'll go over that on Thursday. Okay. Okay, so for today, so we're going to have a system that looks like this. So it has an inlet right here. So some concentration of some fluid comes in here. It has another port, another inlet right here. And over here, it has the outlet. And what we're going to do is we're going to put a probe right here. And that probe is going to test for the concentration. So we have a particular concentration that we want it to be, and we're going to call it C set, and that's the concentration that we want. The concentration that it is at any point in time, because it's going to be a time domain analysis, is C of t. So the concentration that's flowing at a certain point in time. Okay, so the difference between these two is the error. You can call that E of t. Okay, now we've seen the equations for fluid flow before in laminar flow. Let's see where we're at. Oh, good. Okay. All right, so we're all set with that. Okay, and just to remind you what the equations were. So the equations that we're solving, here's the density. And basically, this is a force balance equation, where if you want to think about it, this term right here is like, remember from freshman physics, you have your mass times acceleration equals the sum of your forces. That's what this is. That's what this is right here, but it's mass times acceleration as per unit volume, okay? So that's what that term is. We also have this term right here that accounts for the viscosity. So this is the dynamic viscosity, and that right there is the flow velocity. This is a vector. So we have this. We also have this term right here, dotted into this. And this is pressure. And no external forces are acting. So that's one equation it solves. It also has to solve this equation right here, if you recall. And also for the concentration, here's the constraint about that right there. So this is going to be built into the model. And of course, COMSOL is going to supply this for you. Okay? And so this is simulating the physics all inside there. Right? Now what we're going to do, we're going to have this PID controller to try to adjust this input, so this is the control input right here. This input is constant. We're going to adjust this input such that we achieve a certain concentration that's equal to this, right? And we want to try to achieve it as quickly as possible. You don't want it to be unstable and just oscillate or something like that. You want it to try to get there quickly because you're trying to have a certain type of output and concentration here. So in that case, we have our input velocity here. Is going to be a function of PID. So what PID stands for is proportional, integral, and derivative type of controller. And so let me just draw it out here. If you want to look at the schematic diagram, it looks sort of like this. In our case, we're going to add this. This is like our C set. This is what we want. That's coming in here. What's right here is our C of T, right? These two things is minusing that. Then it goes over here. Here's our error between the two, the difference between what we want and what it's currently at that point right there. And then that goes into the proportional controller is some Kp and times this error, okay? So it takes that error and it multiplies it by this proportionality constant, Kp. That's what proportionality part is. We also have the integral part, let's call that Ki, and that multiplies it by the integral, et. And then we have this derivative part, so let's call that Kd, and that multiplies it by the derivative of this right here, changing in time. Okay, so it goes through all these parts right here. And when you're using a PID, it's up to you to tweak it and determine what these constants are. Some of them you want to use, some of them you may not want to use. Okay? Then you put them all together at the end here. And then what is output right here is your input velocity. That's what you're wanting right here. Then it goes through some kind of process, and this process is all of this, right? It has all this mixture, and we're going to solve this equation for the pressure, the velocity field, the concentration field. We're going to solve that. So I guess you could say this is our model of where we're trying to model. And then you're going to output this concentration right here. And that is what comes back into here as feedback. Okay? Is our concentration as a function of time. And it's like you're probing what your concentration is at that point right there. Okay? So, so basically, this is what we're doing. We're just having our proportionality part, right? Our integral part, and our derivative part. Okay, and so for those of you who have seen this before, this is pretty straightforward, but what's some of the issues that can happen with this part right here? Because remember, you're integrating this over time, and your goal is to have E of t be 0. Because when E of t is 0, that's when this C of t equals C set. And that's your ultimate goal. Okay? But what kind of problem can happen with this part right here?
If there's some sort of blockage and it starts to integrate a response, it might like grow out of
Yeah, exactly. You're integrating, and let me put the limits here. You're always integrating from the initial time to whatever time you're at. So um, there can be some problems where you're like integrating too far, because of some of the issues, like you had mentioned. Um, and even if this goes to zero, like let's say you reach a point where this is zero, it's still integrating. So this whole thing is non-zero, right? Even if that is zero, this one goes to zero, right? So if this goes to zero, this whole term goes to zero. If this goes to zero, the whole term is still not zero yet. Okay? And what kind of problem can happen with this term right here? Hmm? What do you mean?
Like overshoots for bad when you get a change in curve.
Yeah. You have to worry about change because basically this is saying, well, this is a measure of how quickly E is changing. So let's say you have a noisy E, a noisy error, right? And then it takes the slope of that noise. I mean, even if the noise is, like even if it's jumping around by just a very small perturbation, it could be a very fast change. And if it's a fast change, this term is huge. And you're going to multiply it by something here. So that also causes a problem. So these terms like this are hard to really optimize for these kind of controllers. Probably the easiest one, you probably start here. And then this has like a smoothing type of thing when it comes to noise, right? This is pretty bad when it comes to noise. Okay. And just practically speaking, a lot of times there's going to be a delay in. You don't have to worry about it here, but a lot of times you want your feedback to happen very quickly because your system is changing very rapidly, right? So if in that case you want your feedback to be almost instantaneous, but we don't have that yet, right? There's always some type of delay due to the electronics. So most of the time the delay is it could be as small as nanoseconds, actually, okay? If you're using analog circuits. In digital circuits, it could be tens of nanoseconds to hundreds of nanoseconds. But if something is happening very rapidly, you want that feedback to get back as soon as possible. If not, you will have a delayed feedback, and that can cause some stability issues. Okay, so so that's what we're going to try to model today. And to save time, I sent you this file. So go ahead and open that file I sent. Did everybody get it? Okay, cool. Yeah, so we start up COMSOL. Okay, and in this example, I put in, well, it has a geometry in there already, so it'll save us time doing that. And you guys already know how to make that geometry, right? I mean, what this geometry is you have a rectangle right here, a rectangle here, a rectangle here, and a big rectangle. And then at these vertices, these 1, 2, 3, 4, 5 vertices, then you just set your radius of curvature to be what you want. So it's pretty simple geometry, but it's in there, so it'll save us some time making it. Okay, so now so don't do this part. Just load up the file. But what I want to do is just show you what you would do if you were going to start from scratch. Here are the two physics modules that you would put in. You go to 2D, of course, because it's going to be a 2D model. You would go to fluid flow, and then single phase fluid flow, and you would click on laminar flow. You would add that, and then you'd go to chemical species transport, and transport of diluted species. Then you would add that, right? And then when you go to study, you do time-dependent analysis. Okay, that's the only thing. Okay, but that's to set it all up. But we're gonna just load up the file. So let's go to open. Control to, XI. Okay, here we go. And here's the geometry right here. Okay. I guess my drawing sort of looks like it. Okay, so let's start off with the parameters. Okay, so let's key in these parameters, and there are 9 of them to key in. But we'll be using this throughout the analysis. So put in v_n_top. And this is the velocity coming in at the very top of that port right here, up there. And for this right here, let's put in 0.01 meters per second. Okay? And we could type in here exactly what it does. So we could just say velocity, upper inlet. Now here's the concentration that's coming in at the upper inlet. So C_n_top. And that's going to be 1 square bracket mole per meter cubed. MOL per meter cubed. Okay, and that's the concentration at the upper inlet. Okay, we also have initial concentration at this inlet over here. So that's going to be C_n_ just inlet. And that's going to be 0.2 mole per meter cubed. So there's a concentration at the control inlet. Okay, now this is going to be our initial concentration. So C00. That's 0.5 moles per meter cubed. And that's our initial concentration. That's in the chamber interior. So that's going to be all in here is the initial concentration when we first start at T equals 0. Next, we'll have our diffusivity, if I can say it right. This is 1e-4, and the units meters squared per second. Oops, let me go back over here. Diffusivity. Next is going to be our C set. That's what we want, right? C set. So C_set. So at our probe point, we're looking for a concentration of 0.5 moles per meter cubed. Now here's our control coefficients, the Kp, Ki, and Kd. Let's enter those. So our K, well, I'm going to put a lowercase k, capital P, and then control CTRL. The first one is negative 0.5, and the units are going to be kind of funny because remember, what you have to do is whatever this error is, you have time here, right? This is divided by time, and whatever these units are, you have to multiply by these units in order to get the velocity component that you want, the velocity vector. Okay, so that's going to be meters to the fourth power divided by the quantity in bracket mole times seconds, and then square bracket. This is the proportional. Okay, now the lowercase k underscore capital I underscore control CTRL. The next one's going to be -1, and the units, same as the top, but it has an extra second on the denominator. So it's going to be meters to the fourth divided by quantity mole times second squared this time. And then parentheses, square bracket. This is the integral one. And then the last parameter we have is going to be k underscore d, the derivative controller, constant, CTRL. And that's just going to be -1e to -3, and m to the fourth divided by moles, square bracket. Okay, so we got those. So we got our parameters in here, and they look great. Okay, so next let's go to the geometry. Now the geometry is already loaded for you, right? And you can see it clearly right here. But if you want to go back through here and see how it was all put together, here are all the components right here. You had the circular arc, polygon. Yeah. It's actually, it's kind of funny. The way I just showed you about using just 3 rectangles, well actually 4 rectangles, and then putting in your fillets is a whole lot easier than what is done here actually. Okay, so but definitely go through that if you want to see how they did that. Then of course it was converted to a solid. That's why we have this part right here. Next, let's go to our definitions here. Now this is where we told it where to put a probe. Okay. Now it's already loaded here. But what you would do is you would right-click on here, and then you would go to probes, and then you would choose your probe here. And if you click on probe, right here, domain point probe, it has the coordinates. And these coordinates are the coordinates of this point right here. So over 0, up -0.002. And in fact, for example, if you want to move it over to 1, you see that it just moved up a little bit, right? So you can put your probe anywhere you want in this fluid field. And remember, this probe is going to test for concentration. It's not just going to test for the concentration itself, but it's also going to look for the derivative, the change in concentration as well at that point. Okay, so let's look here too. Now here's some point expressions. So here's where we have these 2 points. Point probe expression 1. Here's where we're looking for concentration. Remember that was C. Here's the units of the concentration. And also another expression, CT. Here's the derivative, derivative of concentration with respect to time. Okay. So this is where we define our expressions that we're looking at this particular point where we're probing. Okay, so next let's go to our global definitions. Look at our PDI controller. Now remember, this is already inserted in there for you. If you're doing another simulation and you want to put it into your system to measure, to do your own PDI of something else, what you would do is you go up to Developer, and then you go into Add in Libraries. You go into COMSOL and go to PDI Controller right there. Click on that, and then click Done. And then that's how you would insert it in there. Because typically you don't see this under global definitions. All you would see is this parameters and materials, right? But that's how to add that part in there, okay? And you see the equation right here, and it sort of looks like, okay, I'm missing U bias. So I'm missing this component right here, but I have the other ones there, okay? Here's the proportional part, the integral part, and the derivative part right there. So let's go down here and enter our values. Okay, so so for KP, we had lowercase k underscore capital P underscore control, so CTRL. For the gain, we had K underscore capital I underscore CTRL. For the derivative, we had K underscore capital D underscore CTRL. And for C set, we just had C underscore set. Okay, and everything else, all the defaults are good. So remember, these are the terms, these are the expressions that we had defined up here in the parameters, right? All these right here. So we're just letting the PID controller know what those values are. And in fact, what we'll do, we're going to do a parameter sweep on this guy right here. Because one thing you want to worry about when you're using these PID controllers is what are the right parameters. So we'll play around with this one a little bit and have it select a couple of different values, and then you can see the response. Okay, so okay, fine. All right, so we created that. Next, let's go to our materials. So materials is right here. So let's right-click on materials and just add a blank material. And in this blank material, we're going to tell it what type of material it is. So first of all, let's let's call this fluid. Right? Here's our fluid. It doesn't know what it is yet, but we'll let it know. And let's select domain 1 only. Okay, so it's going to put domain 1. It's only one domain, which makes it real simple, right? But it has a density and dynamic viscosity. That's this term right here. It needs to know what that is, and it needs to know what the dynamic viscosity is. Okay, so let's key that in. So the density is going to be 1.2 kilograms per meter cubed.
Is that the fluid thing that you already
What was that?
You have another fluid in there, materials.
Oh, wait a minute. Oh, yeah. Okay. Um, I didn't realize I saved this too. Okay, yeah. So, yeah, I already did this part for you guys. So that's good. Okay, so if I didn't do it for you guys, you would key in 1.2 kilograms per meter cubed right here, and for this, 3e negative 5 pascals seconds. Yeah, thanks for noticing that. Yeah, so let's go over here and just delete that. We don't need that. And let's make sure it's pointing to the right fluid. Yeah, this is our domain 1. Okay, cool. Okay, so now let's go and set up our physics here. So let's go to the laminar flow first. It's right here. And let's choose our inlet. So right-click on it and choose inlet. And so this is going to define what boundary is the inlet. It doesn't even know yet. So, but we're going to tell it to choose this one right here. So boundary number 1 here is going to be our inlet. And we have to go down to here and tell it that that it has a particular velocity that's being defined here. Now remember, this velocity is coming from our PID controller. Okay? That's well, okay, yeah, that's this right here. That's coming from our PID controller. And COMSOL has its own variables. And its variable for that is this. And when you guys did create, you may have seen this term pop up. It's comp2 point u underscore n underscore control. Okay? So that is a value that COMSOL recognizes. In fact, if we change it around, let's say we put another, I don't know, put a U right here, you see it's a different color now. It doesn't recognize it, okay? But it's COMSOL's own variable for the PID controller, okay? So it's comp2 point U underscore N underscore CTRL. Is it appearing orange for anyone? Huh? Oh, it's orange for you? Okay, maybe probably what happened. Okay, so if you go to the PID controller, did you guys click on create? You did? Yeah, yeah. Just click on create here, and then you see it's sort of like, well, another one popped up, but yeah. So yeah. So whatever variable popped up, you could key that in there.
Can we look up what the like this generated value is, or these generated variables?
Can you do what?
This doesn't like the 3 or the 2. Yeah. Can you look it up somewhere where what it's labeled as?
That's interesting. Okay, so when you guys clicked on create, what value did it show you?
But mine has an informational slot that says the control variable is now available as comp3.u underscore n control.
Okay, and then when you key in,
I tried that.
You also have comp4 down there.
Doesn't like that either.
so it didn't like that either. Nothing? Okay, well, let me try this. So for those of you who are having difficulty with this part, what I can do, let me, let me, yeah, email you this right here. Okay, so, yeah, I think this is the one right here. So this one I'm going to email right here is a little further along. It's like a different stage of it that already has that controller chosen. So if you want to load up that one, and I guess you'll jump ahead too, but but if you're having difficulty with this, you can jump up to that one.
Dr. Boyd,
Yeah,
can you drop down your like component two thing right above the setting?
right here.
Yeah. Can you go to like definitions? Yeah. Then click on variables. Yeah, mine shows that, and then it's yellowed out, and it says I don't have KI control enabled.
Wow.
Mine too.
Okay, so okay, so let's do this. Why don't you? Okay, so I just emailed. I think that was done. Yeah, yeah. So I just emailed you a more full version where the whole thing, where that part of the PID controller has already been bypassed. So let's load up there, and then we'll continue on from there. So we're all on the same page. Let's go to Open, and then go to PID Control. So you guys should have this now. And let's open that. And I do not want to save. No. Okay. Let's pretend it's not done yet. Okay, so so we were at, okay, so okay, so where we were at was at the inlet flow, okay? So what we were doing here at this part is we were choosing this as our inlet boundary, right? That was number one. And then we chose our variable, and that's from the PID controller. Then we clicked, we did laminar flow, and we clicked another inlet. Then that became inlet 2. And then what we chose here was this inlet. Now remember, this is at the top, and this is just a constant flow coming in, right? So if this, remember, we have this variable vn top. That's from our parameters up here, vn top right here. Okay, so that's what we set for this top inlet. Okay, then we added an outlet, and that's this over here. And all you have to do is just define what it is. There's nothing to really set. It defaults to have a pressure of 0, which is what you want. And it's just relative pressure, right? So that's just boundary 13. And then for the walls, they want you to set slip boundaries for just this part, these parts of the wall. So these two boundaries and these two boundaries, these are going to be slipping boundaries. All the rest are like no slip, okay? But these two are slip, and those two are slip, okay? That's why you have these here, each one of those, and you set them to slip here, okay? Now that's for the laminar flow part. And then what we do is go down to your transport of diluted species. And then again, we would add an inflow, and that's this right here. And this right here is from our PID controller again. Inflow 2 right here is just our CN top. And our outflow is, we're going to choose this one right here, and you just have to select it.
Wait, what? What about CN?
Huh?
I want the first.
Yes.
Transport of dilute.
Yeah, yes, transport of diluted species. We're in that one right now.
Okay, yeah, that's what lost us.
Oh, okay, yeah, sorry about that.
Inflows and
Yeah, so we have 2 inflows and 1 outflow here. And basically we're just telling it what the concentration is. The laminar flow was for the velocities. Now we're dealing with the concentration of what's coming in. Yeah, so the inflow, we have our CN inlet. Here's our CN top and our outlet. Now, if you look at our parameters, we define those up here. CN top, CN inlet. Okay. And now the next thing we do is we want to mesh it. Okay, so let's go down to mesh and look at that. So we already put it on finer, but and I think this only takes like maybe like 30 seconds to simulate if it's this fine. Sometimes, like we talked about before, you may want to try maybe extremely coarse. Maybe start off with that. And then just to see ballpark where you're at first, it'll give you a very fast simulation result. Okay. Yeah, but we did finer to try to get finer results. Okay, so that's already done. The next thing we want to do is go into study. So in the study, it shows the parameter sweep. And just to remind you guys how to get that, you go into study, and then you click right here on parametric sweep. And then this thing will appear. And then you can come over here and choose which one you want. And we're choosing this one, which is KP control. And that's this one, just proportional one right there. And we're just setting a list of values. So we're going to try this negative 0.1 and negative 0.5. We could try more, right? But this is just to give you an idea of different values that you can sweep through. You can also set a range too. If you want to click on range, where you're starting from, your step size and your stop, and then let's put that in there too. Okay. Then for the time domain here, we have these 2 sets of ranges. So for the times that we're looking at, this is a range that goes from t equals 0 to 1 second. And this time step is 0.05 seconds. And then after it goes there at this time step is 0.05, then it takes larger time steps of 0.1. Then it goes from 1.1 second to 6 seconds. Okay? And the tolerance here is physics controlled. Then we would go to solver configurations, and for this, we would look at oh yeah, we didn't have to do anything here. Let me see something real quick. Now for the time, I'm looking for anything that you guys would have to change here, because a lot of the values here are defaulted, and they're actually okay for what we're trying to do. Yeah, okay. So then at this point, yeah, it looks like we're all set. So at this point, we would put click on compute, and then you can see your progress bar down here. You may, depending on if you're at the probe table right here, you'll see the time and the concentration, and this is the derivative of the concentration right here, as it's sweeping through time and is solving the problem for you. Okay, so it's done with that. So let's look at the results here. So first, let's look at the velocity field. Do zoom extents. So this is the velocity right here. And again, remember, it went through 6 seconds, from 0 to 6 seconds, right? And if you want to look at the animation, click on animation, click on player, and you can see how the whole thing did over time. You can click on repeat, and then click play, and it'll show you what's happening in time. So remember, here's the inlet that's being controlled. There's a constant velocity input coming in right here, right, that we have no control over. But the probe is somewhere over here, and it's adjusting what this input is to get the concentration just right. And at the very end, it gets there. And that's the output, of course. And each color here corresponds to the velocity at that particular point in the fluid. Okay, so let's stop that with this button. Let's go over to pressure, and you can look at the pressure fields. You could do an animation with that as well. And then you can repeat how the pressure changes. And each line right here, these contours, the pressure is exactly the same along each contour. And the legend over here tells you the pressure for each type of color. Now, the most interesting thing is probably the concentration. It has these streamlines right here. And if you want, you can go down to, expand the concentration, go to streamline, and down here it tells you the density of your lines. It's set at 10. You could change it to 20 if you want to double that and plot that, or a lower number, I don't know. But these are going to be, so this is going to be your streamline field of your concentration. And so if we did animation of that, that's going to be pretty interesting, because basically that's what your PID controller is trying to control at that particular point where you're probing at. Right? And so let's put that in repeat and then play it. And so you can see here where the concentration is, the probe is somewhere over here where you're trying to maintain like around 5, maybe 4 seconds. Yeah, it looks like around 4 seconds if it finally gets to the value that it's trying to get to, and it does so quite quickly. But at that point, then it sort of reached a steady state in its motion. Also, what you can do is this. You can stop it, and you can go back to, let's see here. Let me go to, settings. Yeah, let me show you to find a particular point in time that you may want to look at. So if you go to, let's see here. Let's go to concentration. Here's global. I'm looking for the where you can enter your particular times that you're interested in looking at. See grid, legend, concentration settings. Bless you. Huh. Oh, here we go. Yeah, this, okay, yeah. My little bar right here is covering it up. I didn't see it. Okay, so this right here is at time 3 seconds. So if we said plot, that's what it's at 3 seconds. If you want to see what it looks like at 0 seconds, you could click here and then click plot. And this is what it looks like at 0 seconds. Okay, so remember, all this right here, when it initializes, it has some initial concentration, which is, if you recall, that's our COO, right? And it also has some initial concentration coming in at this inlet and the control inlet, which are the top and the inlet right there. Okay. At 0.05 seconds, immediately after, the next time stamp right here, plot that. You see how things have changed now. Okay, so this probe right here is picking up some information, and it's now feeding it back to the input. And you can just cycle through to the next point and see how it gradually changes over time. Okay, and so again, that's how to do that part right there. So now, if we want to look at this inlet velocity right here, remember we had 2 types of values for KP, and that's the proportional controller. We didn't change these at all. We kept those steady, right? I think that was like at -1, and that was like -1e, -3, something like that. But this is the one we're modifying right there. So the first one, the blue one, was a value of -0.1. That's this one right here, where it overshoots, and it takes a little while to settle down. This one right here is at -0.5. And as you can see, it reached its optimal value much faster than this one. And of course, if we had more values than just these two, simulation would take a little longer, but you would be able to easily find what is the value of where it stops oscillating and becomes, well, this is more, much more stable than this one right here. And something more like this is what you want to achieve. Okay, so, and remember that was back when we had set the PID controller for the KP values. I'm sorry, the parametric sweep right here for the KP values. Okay. Okay, so any questions about this example? Yeah. Yeah, exactly right. And in fact, if you want to do a sweep, you would just click your range right here and tell it to sweep, and you have a large family of values, and you would see exactly when was the onset of something you're interested in. That's right. And also, too, this KP value is the one that's, I guess, it's the one that's most easiest to to have control over, I guess, where you can. It's, I would say it's the one that's most well behaved, right? But you can also sweep these other parameters too, Ki and Kd, to find out what they do and how they affect this as well. Okay, so all right, so in our last 5 minutes, let's see. I did want to start another one, but I'll just talk about it. The one we're going to do on Thursday. Okay, so what we're going to do on Thursday is something that we did before, but we're going to analyze it a little differently. So on Thursday, we so before we had looked at these folded flexures, right? Where it has a structure that looks sort of like this. Here are the flexures. It has a wider beam right here, which is actually more rigid than those. Comes back here. Then it has this sort of like dog bone looking structure, which is more like a proof mass. And it's symmetric. So you have this on the other side too. Oops, I'm drawing it wrong. And then it has some comb drives right here. And remember, these are variable capacitors. And so what we'll look at is we will demonstrate that the force that these variable capacitors apply onto this proof mass here is actually independent of the overlap of the comb drive. Okay, so this part right here is going to move back and forth. This right here is like a stator, and it moves back and forth like this. But regardless of what the engagement is going to be, the force on these comb drives is going to be identical. Okay, it all depends on your voltage, and it's proportional to the voltage squared. So what we'll look at is this is anchored. That's anchored too. So everything with the x's are anchored. We'll look at how to determine the energy of the system that's stored in the electric field. We'll also look at the energy that's stored in the mechanical structure itself as it goes from side to side, and we'll compare those things. We'll also look at the charge density, and we'll show that if you were to enlarge this comb drive right here, that one comb finger, and here's the other one on top of it, the fields look kind of interesting, where the fields that are like in between, the field lines are quite parallel to each other, quite constant. But as you get to the edge right here, they start to flare out a little bit, like this. Okay, it's like a fringing field effect. So in here is like a parallel plate capacitor, and we can determine, what that is even just analytically by hand. But out here it gets a little more complex where these fields are fringing. And what we'll find out is that the concentration of charge is quite constant along here, and then it bunches up on the ends right here. Okay, and we'll be able to plot along this surface the, like if you were to take this edge right here and just plot the charge density right there, it'll look sort of like this. When it comes to the edge, it'll like peak up like that at this point in the edge right there. But it here looks like just a simple parallel plate capacitor model. But that's it for Thursday. Okay. All right, guys, that's it for today. See you guys next time.